Gabriel had asked me previously if we were going to get an equation sheet for exam one, and I told him I would look into it. I found an old equation sheet that I've used previously, so I've gone ahead and uploaded that. I'm 99.9% sure that I'm going to wind up changing some of the things here because right now everything is only related to silicon, and I intend to mix things up a little bit or whatever. So I'll probably have something similar to this with regards to equations, except that I'll also wind up including like tables like you've seen in your homework problems and all of that kind of stuff so that you can apply the equations to different materials and all that kind of jazz. Anyway, so consider this to be just a draft, and then I will correct things later. Also, I no longer use capital K for Boltzmann's constant. I use lowercase kb and things like that. So I'll try to make it consistent with the way that we've been doing stuff. But it does appear that I intend to give you an equation sheet for exam one. I know for sure I'm giving you an equation sheet for exam two, and we'll see about exam three. But anyway, just wanted to make you aware of that. It's available on Canvas. If you go down to where it says exam one, whatever class meeting that is, it's the only thing uploaded there presently. All right, so metal semiconductor junctions. Going to be drawing lots and lots of energy band diagrams today, just giving you fair warning. I don't like the look of that end. All right, so metal semiconductor junctions occur whenever a metal is deposited on a semiconductor material, like we saw when we talked about how physical PN junctions are formed, right? These junctions can either be a rectifying junction or an ohmic junction, depending on the work functions of the metal and the semiconductor material used. So generally speaking, if phi m, where phi is the work function of the material, is greater than phi s, so the work function of the metal is greater than the work function of the semiconductor material, we have what is called a rectifying contact. We'll go into more detail about what this means in a moment. And if phi s is greater than phi m, meaning the work function of the semiconductor is greater than the work function of the metal, then we have an ohmic junction. So we are going to start by looking at rectifying junctions. So here I'm going to have energy band diagrams for a metal. So I'll put the metal over here on the left. So we're going to have something like this. Where this is our Fermi level for our metal. And everywhere below the Fermi level is completely and utterly full of electrons. And then this distance from the vacuum level to the Fermi level is our work function of our metal. So the work function represents how much energy it takes to move a charge carrier from the Fermi level of the material to what's called the vacuum level, meaning you're literally stripping that electron out of this material entirely. Okay, so that's what the metal looks like. And then over here on the right, let's put a semiconductor. So for a point of reference, we're just going to put the top matching up. And this is going to be for N-type semiconductor, generically. This dashed line right here is the Fermi level for our N-type semiconductor. This is the edge of the conduction band. This distance is our electron affinity. This distance is our work function. Here is our valence band. And our valence band is completely filled. And then we're going to have some electrons here up in the conduction band, since this is an N-type semiconductor. Okay, so this figure effectively represents how what the two materials energy band diagrams are going to look like before we bring them into contact with each other, with the vacuum levels of each of the materials aligned. The metal is completely full of electrons up to its Fermi level EF sub m, and the valence band of the semiconductor is full of electrons, with some free electrons available in the conduction band as well. Okay. So when we bring these two materials into contact with each other, meaning we deposit metal on top of our semiconductor, what we are going to see is that the Fermi levels of both of the materials are going to align, and that the energy bands of the semiconductor will bend to accommodate this. So what we have here, like I said, is before contact. And then down here, we will have after deposition. Okay. So here's our metal. Once again on the left. And let's see. So here is EFM. Here is EFN. Our bands are going to curve to take this into account. And then somewhere down here, something like this. Here's EC, EV. All right, so here's our band bending. Again, this occurs because we need the Fermi level of our undoped junction to be constant across the entire duration of our device here. And so we see that the band of the semiconductor bend in order to accommodate the structure of the metal. Let's look at a couple of things here. Let me put those electrons back in here so we can kind of see them. Okay. So one thing that I want us to observe is that our metal will always have much more free charge carriers than our semiconductor material will have. Okay, because every single atom in our metal is going to contribute at least one free electron, up to 3 free electrons, because that's how metals work. Whereas only 1 part per million to 1 part per billion or so of our semiconductors will have a free charge carrier, depending on how we dope this thing. Okay, so the metal always has more free charge carriers than the semiconductor material. What does that imply about the width of the depletion region for a junction like this? It is non-existent on the metal side, effectively. The depletion region only extends into the semiconductor material, right? So in this case, this is our width, W naught, like so, extending only into the semiconductor material. This height, so how much our vacuum level bent, is the difference between our metals work function and our semiconductors work function. And this is going to be equal to Q times V naught, the built-in voltage of this junction. We're also going to have a barrier potential here. So this is phi B, and it is equal to phi M minus the electron affinity of the semiconductor material. So effectively what's happening here is that electrons in the conduction band of the semiconductor material have higher energy than electrons in the metal. So we're going to see electrons from the semiconductor try to move into the metal because there are free energy states down there. But we are also going to see, let's see, hold on here. See, the semiconductor is losing electrons to the metal, so it's gaining positive charge, while the metal is accepting those electrons, gaining negative charge, meaning that we're going to form a space charge layer. So I'm going to put a bunch of plus signs over here to indicate the stored positive charge on the semiconductor side of the junction, and negative signs over here for the stored negative charge, because we're effectively losing electrons into the metal, right? The stored charge develops a built-in potential V naught, which stops diffusion once equilibrium is reached. So it's a very similar process to what we saw in PN junctions. Electrons that are trying to move from the metal to the semiconductor see this barrier potential phi B, which is larger than Q times V naught. This barrier right here is called the Schottky barrier. So effectively what this Schottky barrier is making sure that electrons can't diffuse from the metal into the semiconductor, because as I pointed out earlier, the electron has a whole hell of a lot, the metal has a whole hell of a lot more electrons than the semiconductor does, meaning that we would expect diffusion to occur from the metal into the semiconductor, but they see a very, very large energy barrier that's preventing them from diffusing. Right, so it's hard for electrons to jump over there. As we mentioned, the depletion region of the junction extends only into the semiconductor side of the junction. So we would have something like this. W naught is equal to twice epsilon divided by Q times our barrier potential, our built-in potential V naught, divided by ND, all to the 1/2 power, or just square root of that thing. And from this, our junction capacitance, Cj naught, is going to be Q epsilon A squared times ND over twice our built-in potential V naught, square root of this whole thing. So here are our parameters for our unbiased junction. So again, let's recap things. You know what the work function for the metal is, which is literally something that we can look up in a table. The work function for the semiconductor, the difference of these things divided by Q gives us our built-in potential D naught. Our barrier potential is going to be the work function of the metal, again, something that we can look up in a table, minus the electron affinity of the semiconductor, also something that we can look up in a table. Tells us what our Schottky barrier height is going to be. The width of our unbiased depletion region, we have a one-sided junction effectively. So we only have a one-sided depletion region. It extends only into the semiconductor material given by this right here. And lastly, our unbiased junction capacitance due to the stored charge on both sides of the junction is given by this relationship here. Yes.
The barrier is 5B.
5B. Yes. All right, so when an external voltage is applied to a rectifying metal semiconductor junction, the polarity of the applied voltage can either increase or decrease the probability of majority carriers electrons diffusing from the semiconductor into the metal. So effectively, if we were to forward bias this junction, what would we expect the energy bands for the semiconductor to do? Would they raise or would they lower? They'd raise up, right? So we would see that these bands here would shift up depending on how much we forward bias this thing, making it easier for electrons to overcome this gap. The electrons from the metal will practically never be able to overcome that phi b term. It's always there regardless of how much we shift the right-hand side up or down, but we're making it easier or more difficult for electrons in the conduction band to move over to the metal by biasing this thing. Okay. So the current density of this diffusion is given by the following expression. J sub n is equal to Q V n sub c times the exponential of negative Q phi b over kBt times the exponential of Q times our bias voltage divided by kBt minus 1. So just really quickly here, V is the velocity of carriers, in this case electrons, and NC is the density of states in the conduction band of the semiconductor. It's related to material properties and all of that kind of good stuff, which is what we would expect, but it's also related to how quickly we're able to move the charge carriers, which is also dependent on our applied voltage. So effectively, we have this constant term outside here, then we have the probability of overcoming our barrier potential, and then the probability of overcoming this potential for diffusion. So it's a process like so. We could simplify this thing as J sub n is equal to JS times EXP of Q V bias divided by KBT minus 1. Where this whole thing right here is just JS. So what does this equation look like? Mr. Finch, you're smiling at me. IV characteristic curve for PN junctions, literally the exact same thing. The only difference is what defines our reverse bias saturation current density, JS, right? So for a PN junction, it's all about probability of diffusion, diffusion coefficients, and the diffusion lengths. For this metal semiconductor junction, it's the density of states and how quickly we can make the electrons move, again, multiplied by the probability of overcoming the Schottky barrier potential 5B. But generally speaking, a rectifying metal semiconductor junction behaves exactly like a PN junction does. So when we have a rectifying semiconductor junction, or excuse me, a rectifying MS junction, it's just a diode as well, okay? Now let's look at, or actually let me plot this out. So our IV characteristics are going to look something like this, which is identical to our diode relationship. So we have V bias on this side. We have an exponential increase in current over here. And something like this, where once again, our current over here is typically measured in milliamps, and our current down here is typically measured in nanoamps or smaller. Mathematically, they behave in practically the same way. So everything that we did here was with an N-type semiconductor material, right? Is it possible to get a rectifying junction with a P-type semiconductor material? Yeah, why the hell not? It only depends on what our work function difference is, right? So if the work function of the metal is, go back here so I don't screw this up. If the work function of the metal is greater than the work function of the semiconductor, we are going to get a rectifying junction. If the work function of the semiconductor is greater than the work function of the metal, we're going to get an open junction. So we can play around with different materials in order to figure out what we're going to get, right? So if we're trying to form a diode using a PN junction as our rectifying junction, we have to be very careful about what types of metals we select to use for the leads in order to allow us to apply voltage and current, because we don't want to have a rectifying junction effectively on top of another rectifying junction. That's not the purpose here. We would want an ohmic contact in order for us to pass current in both directions effectively for metal to be, for current to flow through our PN junction. So let's talk now about ohmic contacts or ohmic junctions. So let's say that we have a metal over here on the left, different metal than before, which should be fairly obvious because here is our work function for our metal. phi m. Here's EFM. And then all of this is full of electrons. And then over here, we're going to have yet another N-type semiconductor. Did not mean to erase that. Excuse me. Here we have EC, EFN, EV like so. Our electron affinity, chi, the work function for our semiconductor, phi s, and we have something like this. And this is once again what things are going to look like before we deposit our metal onto our semiconductor. So when we bring these two materials into contact, we're going to find that our Fermi levels are going to line up again. So let's look at some things, right? So we have electrons in this high energy state here. And then the Fermi level here is lower, right? So what we're going to see in our ohmic junction is that electrons will be able to move from the metal into the semiconductor material. So when we butt these guys up against each other, here's EFM, EC, EFN, sorry, forgot to draw my free electrons up here. It particularly matters. We're going to find that electrons can easily move from the metal into the semiconductor material. So the metal is losing electrons or gaining positive charge, and the semiconductor is gaining electrons or gaining negative charge. And this results in the formation of what we call an accumulation region. So instead of having a depletion region devoid of charge carriers, we have an accumulation region that has extra charge carriers available. The stored charges develop a built-in voltage potential, which will stop electron movement from the metal to the semiconductor once equilibrium is reached. So over here, we're going to have something like this. So here's our metal. Like so. Here's EFN. Excuse me, EFM. EC, EFM, this. We have electrons over here in our conduction band and all of that kind of good stuff. Here is our built-in voltage. So phi sub S minus phi sub M is going to be Q V naught. This little difference right here is our barrier potential, phi B. And what can we say about what's going on here, right? Well, our electrons in our conduction band don't really have to do a whole hell of a lot to get over here into the metal. And similarly, electrons in the metal don't have to do a whole hell of a lot to get over here into the semiconductor, right? So if we were to bias this thing, under forward bias conditions, excess electrons in the semiconductor can easily flow back into the metal because we're just raising this potential up. So it makes the electrons over here in the semiconductor more likely to move over here into the metal because they see significantly lower energy states over here. Whereas if we were to reverse bias this thing, electrons in the metal would see lower energy states available in the semiconductor. So instead of having a one-way direction for current flow like we saw for a rectifying junction, we have a two-way direction for current flow, right? So we no longer have rectification, we have current able to flow in both directions, which we could quantify with a simple resistance. So the resistance of a ohmic contact metal semiconductor junction is the length of the junction divided by Q times mu N times ND times the area of the junction. All right, we're done for today. Grayson. I can't remember off the top of my head, and it also depends on, so you have to look at both the metal and the semiconductor because it's the difference between the work functions of those two materials. So for semiconductors, if we're looking for a single element semiconductor, you know, we're looking at, let's say, silicon, germanium, and carbon. The metals that are commonly used, I think like aluminum off the top of my head, I know gets used a lot. Zinc, tungsten, where's W? Oh, way over there on the left. Yeah, I remember tungsten being used specifically. It's been a hot minute, but effectively any metal and any semiconductor can work. We've just got to play around with things until it behaves the way that we want it to. And that's all based on what the work functions of the two materials are. North, I believe you had your hand raised a moment ago.
Is that
RMS.
So what is that?
The resistance of the metal semiconductor junction. Right. The length of the device, effectively. So the longer it is, the more resistance it should have, which is exactly how we expect resistance to work. So just as a quick thing here, this is Q, this is mu, this is N, the number of electrons in the N-type material. What's Q times mu times N? Conductivity. R is equal to L divided by sigma A is literally something you learned in, I think, Engineering 121, and we definitely covered it in Circuits 1 as well, except that we called this 1 over Q times mu times N rho for the electrical resistivity, and we put it in the numerator. This is literally just fundamental definition of resistance based on geometry. Anything else? Yes.
Around 2 o'clock. Back, on the phone.
2 o'clock I have senior design. So I'm in class for the rest of the day. That being said, we're wrapping up 30 minutes early. So if you want to talk to me, come talk to me in a minute. What's next? Yep.
She says that, depending on if the graders allow it. For performance, is there something on that?
Did you ask? Why would I ask?
Oh, I was just wondering.
Yes.
Take home portion cost, or is it just?
Take home portion, very much so. So the take home portion of the exam will be a small design type thing as well as the theory questions. Where I'm expecting you to write out, paragraph or something explaining something. So good questions for that something would be the difference between avalanche breakdown and Zener breakdown. Let's see. Is built-in potential dependent on temperature, and if so, explain how, things like that. Whereas the in-class portion will be similar to homework problems. Yep.
If we messed up the homework once, can we still turn in a 52? Or is that-
Ask the graders.
Oh, do you know, or do you have like an idea? Are you gonna post homework 3?
Yeah, so homework 3 is going to be posted sometime today. Homework 3 will be on biased junctions. So both forward bias and reverse bias. I realized this morning I should have posted it this weekend, but I didn't feel well, so I didn't do it. So it'll be due this Friday, which I think seems like a reasonable amount of time for like 4 to 5 questions. I have not heard anything from IEEE, nor have I heard anything from Eta Kappa Nu, so I assume there will be at some point, but I don't know what that point is. Daniel says we, and I'm assuming he means IEEE, should be having a study session tonight in IESB 224 from 7 to 9. Thank you, Daniel.
He's just the only one in the room.
Anything else?
No.
All right, so Wednesday, we're going to start talking about diodes as devices. So less physics, more circuit analysis. Hooray.